So back to random groups at density model. Remember that what we were proving. So we have we are in the density model of random groups, and the density parameter is strictly less than 1/2. And we analyze the case. We would like to prove linear isoperimetric inequality for all with high probability for all reduced one-component diagrams over this presentation. Okay? Is it clear where we are? So this is what we did last time. So we analyzed the situation when so we have our, let us see, some one-component diagram. These are relators you read, etc. And we consider the internal length, everything which is internal. This was our length L, or a word. This is for given relators, and now we can choose relators, and this is, we estimate it like this. And the probability that we can fulfill this diagram, to make this diagram, was estimated like this last time. And here we see immediately that when we have this condition, L strictly greater than dt number of faces, this is number of faces in the diagram, then this quantity decreases exponentially when t goes to infinity, right? So the probability to fulfill this diagram is exponentially small. This is what we did last time. And now we will, so let us write, so in this situation, what we had, so the under the condition that L is strictly greater than dt, d is our density parameter, length of relators, number of faces in the one-component diagram, then the probability we estimated is this is I just write so if I put this little epsilon into the formula, I will get epsilon t delta, what is of course smaller or equal to epsilon t, right? I can write the same. Okay, so in this situation we have this as a result, and let us analyze the other situation when L is strictly less than this quantity, right? Let us analyze this. So again, this is I just write what is our situation, and I wrote L is strictly less than dt cardinality of delta with a little epsilon, right? Less or equal. And in this case, I analyze what is the length of my boundary of the diagram. So I'd like to analyze the length, the length of the boundary of the diagram. This is my what I read here. This is my boundary, and I'd like to analyze the length of this. And it is very easy. I know that each relator has a length t, right? And I know the internal common, the total length is L. So if I count, each relator has length t. So this is, I counted here, t times the number of relators. But each time when I count this common thing twice, right? And I have to remove it because I'd like to count the boundary. Okay, so it's really obvious. So the length of this boundary is T delta minus 2L, and I am in the situation when L is at most this number. So I just put it inside, and it gives me this formula. Okay, and let us take just so what we have. For L strictly less than dt delta, actually we have the formula. I will keep it for the discussion. Right, and if so we have linear isoperimetric inequality, right? This is what we wanted. See the title of the slide. We wanted area is smaller or equal some constant times perimeter, right? Area is a number of faces, so we have this, and this is our constant. Of course, we have to put it. T is also a constant, right? So so if we choose, for example, epsilon like this, I can choose it. Remember that our density is strictly less than 1/2. I have a very nice, even a little bit nicer, but in detail it is this linear isoperimetric inequality. So what we have? So we have this situation, right? Either this given delta satisfies linear isoperimetric inequality, and this linear isoperimetric inequality is exactly what we get, or the probability to fulfill this diagram is exponentially small, right? This is what we had before. So this is our situation, but remember, we started, okay, let us see. So first, I'd like to make a remark that actually this linear isoperimetric inequality we get, it is optimal one. We cannot do better. In this model, we are in the density model. So remember, we proved already that what happens for small cancellation in the density model. And this is a summary of what we proved, that if the density is smaller, strictly smaller than λ/2, we have small cancellation, classical one. If it is strictly greater, then we don't have. This is what we proved using dimension, remember. Okay. So let us use this. So take so our d is strictly greater than this number. You see, this is just a trivial, right? I put a 2 everywhere. So d is bigger than d minus epsilon. Epsilon is some positive thing. Okay. So I use this using this formula. So my lambda is 2d minus 2 epsilon. Okay. So by this argument we had, I have that I don't have small cancellation with this constant. So what it means that I don't have small cancellation with this constant, it means that I have a piece which is long, right? So I have two relators which have common piece, and this common piece is long. So it means that, and actually I know how long it is. So it means that I have this situation. I have some r, some r prime, and I have this common thing. This is my say delta prime. That doesn't matter. Some diagram, and the length of this is bigger than the constant I have chosen. So 2d minus 2 epsilon times the length of, say, r. Okay. So I have this diagram which has exactly two faces, exactly this diagram. Okay, let us calculate let us calculate perimeter of this diagram. As before, it is t times the cardinality. This cardinality is 2 here, minus 2 the length of the arc. So this is this arc. Okay. So, and I know the length of this arc is at least this 2g minus 2 epsilon times the length of r. So, and the length of r, this is my t, right? So I do this little computation and I get this thing. And so what it means? It means that for this diagram, smaller or equal, I have 1 minus 2g plus 2 epsilon times the size, right? The size here is 2. This is where it's true. And you see immediately that these two inequalities, so for this diagram, this specific diagram, which we have because of small cancellation, no small cancellation, and this inequality, so they're the same, right? So it shows optimality. Okay, so this is to see that it is optimal what we get. And now again, so what we have, what we just computed, we estimated that either given delta satisfies linear isoperimetric inequality, what we wanted, or the probability to fulfill it is exponentially small. But remember, it was forgiven, so I started with some abstract Van Kampen diagram, right? Abstract picture, and then I tried to fill this picture by relators. And I estimated how I choose words, how I choose letters, such that they are combined, and so on. So I started with some fixed when I estimated this probability. So now I have to estimate how I can choose this abstract Van Kampen diagram. Okay. We will do it, but first let us see this very deep result, completely really major result in the theory of hyperbolic groups. It's what it says. It's local to global principle. But first, I'd like to say why. Before reading this result, I'd like to say why. So we estimated something for a given abstract Van Kampen diagram, okay? But what we would like to prove hyperbolicity. So for hyperbolicity, as I said, actually we would like to prove that any reduced Van Kampen diagram over this random presentation will satisfy linear isoperimetric inequality, right? But any reduced diagram, it's a lot of diagrams, infinitely many. Okay, because of course we have finitely many words, exponentially many, but you can glue them and so on, and you don't know. They can be very big. You can repeat the same relator many times. Okay. So you have infinitely many, and how you have some estimate. We have some estimate on the probability, but how we combine all this? Okay, we have a problem. We cannot proceed. But to proceed, we need this result. And this result, what it says that if you would like to check linear isoperimetric inequality over all diagrams, in fact, you don't need to check over all diagrams. It's enough to check only finitely many. This is why it says local to global. So if you check for finitely many, it will be enough to conclude hyperbolicity. So it is very deep result. We will not prove it. It takes some time. We will just use it. Okay. So let us read. So for every alpha, there exists some constant, and depending on alpha, and alpha prime, such that if a reduced Van Kampen diagram with this number of faces, k of alpha number of faces satisfies linear isoperimetric inequality, then any reduced one compon diagram satisfy, but probably with a different constant here. Okay, so constant change, but isoperimetric inequality remains linear. Okay, so for given alpha, we will find some constant such that it's enough to check finitely many diagrams for our linear isoperimetric inequality. Okay, finitely many exactly with this bound on the number of faces. Okay, do you understand the point? It's really a crucial point. Number of relators is finite, but when you do this tessellation on the plane, it can be very big. So you have infinitely many diagrams. Okay, so but this result allows us to check only finitely many. Great. So let us take this is for every alpha. Let us take a concrete alpha we have in our situation. So remember, we are in the situation then the density is smaller, strictly smaller than 1/2. This is some number. Then applying this local to global theorem, I will find some constant k. And then I'd like to estimate how many diagrams I will get. Okay, k is the bound on the number of faces in the diagram, but I can glue them and right. So I need to estimate how many I have, because my estimate on the probability is on a given abstract one compon diagram. Now I have to estimate how many times I can produce this finitely many things.
So for this local to global theorem, you don't have a presentation at all, or you fix the presentation?
No, we don't. We have generators.
So generators, set of generators is fixed.
Right.
Relations are not.
Right. Right. So right. So okay, let us. This is a number we need to estimate. This is a number of abstract one compon diagrams which we can get, and then we have to fit. Okay. So is it clear what we are doing? Right. So this is the number of reduced abstract one compon diagrams. So no relators. It's just as we discussed before. This is abstract thing, a planar graph. Okay. Planar a thing like this, which we will fill after that. Okay. So the probability that such a diagram is fulfillable then will be, we will multiply. So you see this is this number. I just put it epsilon like we have chosen. So it is the same formula, this one and this one. Okay. And I have to multiply by number of possible abstract one compon diagrams. So this number I need to estimate, because you see I know that the number of faces is maximum k. Each face has length, the length of each relator is t, but I don't know how many. So if this number is very big, I'm a little bit in trouble, right? Because this is decreasing exponentially, but this I don't know. So if it is very big, then I don't have a result. Okay. So I really need to estimate this number. Again, it's a number of reduced abstract one compon diagrams with number of faces at most k. It is something very, it's just a planar graph. Okay. Let us estimate this. It's just a planar graph. So how we do this reduced abstract one compon diagram? It's a planar graph, and we have to choose. Imagine it's a picture like this, a planar graph, and such that for each face we have to choose the length of these common things. Okay, but first it is a planar graph with which conditions? number of faces is at most k, and each vertex has a degree at least 3. Right? Each vertex. It's really the abstract thing what I consider now. So here probably there are vertices of degree 2, but we don't consider this graph omega. I'd like just to count how many possibilities I glue these abstract things. Okay? So I have a planar graph. The number of internal these regions is at most k, and each vertex has degree at least 3. Right? Then I'm very happy with this situation because I can estimate a number of such graphs. I will do it here. Right. So what I would like to explain now, it is this implication. Euler formula implies that the number of edges is at most 3k. If it is obvious for everybody, I will not do it. But is it okay? Or it's okay. Just use Euler formula and the fact that so when you count edges, 2 times the number of edges is less or equal to 3 times the number of vertices. Right? Because every vertex is degree at least 3. So you put this into Euler formula. Number of vertices minus number of edges plus number of faces is equal to 2. And you get some estimate, which will not be 3k, just because the number of faces here, for us, it is k. But in the Euler formula, you also count the external. So you put k plus 1, and you get this thing. Okay, so it's quite obvious. Great. And then using, okay, so this is we did. And then we have to, if we have a given graph like this, then we have to choose. So we know now how many edges on this graph. And for each graph, we have to choose the edge length. It is, again, it is this length we would like to choose. This length. Okay? So how many possibilities? Well, because we know that this is length t, then we estimate t to the power 3k, right? It is very rough estimate, but it's okay for us. Okay, great. And then, of course, we have to choose, again, what we are doing, it is abstract Van Kampen diagram. So we have to, if we choose already the length, we have to choose also a beginning and an orientation, where we will read after that our relator. Okay, so to choose the beginning, we have t possibilities. Orientation, of course, like this or like this. This is why we have 2. And right. And remember, in the abstract Van Kampen diagram, because we don't have yet the relators associated to each face, we have just integers. Okay, and these integers from 1 till the number of faces, and number of faces is k. This is why we have this k here, right? So this is what I explained just for each face, and we have k faces. This is why we have the power here. Okay, so okay, great. So this is enough to estimate our number of this abstract planar graphs, and this is polynomial in T. So there is a lot of k, but remember, k is a constant. So we don't care. So it is polynomial in T, and now we are happy because we can multiply. And now we know that here this number is too small. So the main factor is this one, exponential, which decreases to 0 under these conditions. Okay? So we are done for hyperbolicity. Now, it is very, right, it was a nice, I think a nice proof. And now tell me where is the mistake. There is a really crucial mistake somewhere, conceptual one. Not in the, of course, like this you cannot follow all these little computations, but remember, conceptually what we did, we start with an abstract Van Kampen diagram. We try to fulfill it. We estimate the number, the probability that it can be fulfillable, or under these conditions on L. Or if L satisfies this, then we get a linear isoperimetric inequality. And at the end, we estimated the number of these planar graphs to estimate the number of abstract Van Kampen diagrams. So where is the mistake in the conceptual thinking? So actually, this was the proof of Gromov. So there is a, I don't think, I'm sure he knew the mistake, but right. So what we don't take into account in this argument that actually the same relator, I said it quite quickly, but actually the same relator can appear several times, okay? So we cannot do this like we did, like everything is independent, okay? So we should really take care of, you imagine, it's complicated. It's possible, but complicated. I will not do it. It will take another 2 hours. But it is also very combinatorial, so we have to take care of possibilities when the same relator appears several times. Because once you have chosen it, you have less places, right? Because other things are already fixed. So one has to do it, and this was why for this theorem we had 2 names. So first proof of what I explained, it was by Gromov, and then Olivier fixed this little situation. Great. So this was for hyperbolicity. So remember, we already proved this part. Now we proved, I gave a sketch of the proof, of course, of this part, hyperbolicity, and now why it is actually non-trivial, because we did probably it's a trivial group, and then of course it is hyperbolic, right? So why it is not trivial in this situation when we have density strictly less than 1/2? So the fact that it's non-trivial, it's quite easy to see immediately from what we proved. So okay, so what we proved is that every reduced Van Kampen diagram satisfies this linear isoperimetric inequality. In particular, it satisfies this, okay? So then take the Bohr of radius of this radius in the free group, and this result says just that this ball injects in the Kelly graph. Okay? Is it clear why? If it doesn't inject, take this loop, and so if it doesn't inject, it means that there are 2 points in this ball such that they go to the same in the Kelly graph, right? But in the ball, there is some path between them. So you have some loop in the Kelly graph with some path here. So it is your Van Kampen diagram. You feel it. And actually, because of the length, you can use this linear isoperimetric inequality. This is why we have chosen this one. So this Van Kampen diagram, what I quickly explained, there it has the perimeter 0, right? So it is a contradiction. So you cannot have it. So it injects, but of course the ball in the free group, it is non-trivial, so there are non-trivial things. So the group is non-trivial. Okay. The other thing to prove that it is infinite, it's more complicated. I say it quickly. Probably some of you don't know these words, but actually it's not complicated if you know all these words. But it goes like this. Actually, this one-component diagram is aspherical. What it means? It means that I cannot draw it on a sphere. And it is reduced. We are talking about reduced, so I cannot draw it on a sphere. Why? Again, because of linear isoperimetric inequality. On a sphere, there is no boundary. So boundary is 0. And then it is contradiction to this linear isoperimetric inequality. Okay? So we have automatically that all these one-component diagrams we have, they are aspherical. And then remember the picture you had, I think, yesterday in the other lecture. You have a one-component diagram, and then you can draw it in an interesting way in the Kelly graph, even in the Kelly complex. Okay? So do it here, imagine it like here. So it will mean that also Kelly complex is aspherical. And this implies, depending on your knowledge of cohomological dimension, this immediately implies that it is at most 2. And this is also immediately implies that G is infinite, because when you have torsion elements, cohomological dimension is always infinite. Okay? So this gives us this fantastic theorem, which is a phase transition theorem for hyperbolicity at the density model of random groups. But again, I'd like to mention that this was a sketch, right? We didn't consider distinct. We really, this is a sketch when all relators are distinct. Great. So let us go now. This is a summary. So what we did, we proved this phase transition theorem at the density model. We had some examples of other results in the density model for small constellation. I mentioned quickly for non-planarity of the Kelly graph. Okay, and this is a model which is different from the model we considered before, genericity model. Here, the number of relators you take is exponentially many, not fixed, depending on the density parameter. They all have the same length, so this is really used in all arguments. It's a little bit, yeah, you can like it or not, but all the relators are of the same length. And in general, there is no small cancellation. Remember, if you go more than at density more than 1/12, you don't have small cancellation anymore. Okay. So it is quite interesting. You can take your favorite group property and try to see where is your critical density. Okay, it will be certainly strictly less than 1/2. Okay, great. Let us discuss now a different model. So up to now we had 2. Let us discuss a different model for randomness. A topological model, and for this we have to define what is called a space of marked groups, and I will do it in a very quick way, a little summary. So we fix a free group, again Fm, and consider all normal subgroups. This is your space, because remember, finitely generated groups, these are quotients of free group. Right? So it's enough to consider just, if I'd like to consider my group, it's enough to consider the normal subgroup which is in the free group, which defines this group. Okay? Is it clear? Okay, so this is my space. It is a space of normal subgroups in a fixed free group with a fixed generating set, M generators. So in such way, I consider also all quotients, right, of Fm. And then I define, on this space, I define the distance to have topology. And the distance will be the following: exponential function minus and I count this maximum k such that balls of radius k in this normal subgroup and in this normal subgroup coincide. Okay? When I consider on the ball of radius k in this normal subgroup and this normal subgroup, they are the same actually. Then I say that the distance between these two normal subgroups is exponential minus a maximum such a k. So you can, if you prefer to see it in on a graph, on a Kelly graph, it means that so the distance will be exponential minus k when on the ball of radius k minus 1 divided by 2, because it's a radius. Yeah. These two balls will be the same for one group and another group. Okay? Is it clear? Exactly the same as labeled graphs. So again, I have two groups, two Kelly graphs, and I take balls of radius k minus 1 divided by 2. If these balls are exactly the same, I say that the distance between these two groups is exponential minus k. Okay? So in such a way, I define the metric space on my all m-generated groups. And this metric space is compact. Why? Okay, so this is a subset in a free group. Free group is fixed. Okay? Consider the space of all subsets in the free group. This is just a product space, right? And there is a Tikhanov theorem which says that we can define topology, right? And product topology, we can define topology, and because each subset is compact, product is compact. Okay? This is for the space of subsets in the free group. But here we have not all subsets, we have normal subgroups. And another step, we have to see that this space of normal subgroups is closed. Okay? And then closed subset in a compact space is compact. So we do, you see, we start to do general topology a little bit. Okay? Great. It is ultrametric. This is, you can just check by. So ultrametric is stronger than metric. So just instead of triangular inequality, you have maximum between two. Okay. So you can just check it by definition, and it is separable space. Okay, it's a compact space. So. Great. Now, okay, the next attempt to define randomness is to use this topology. What we did before, it was like more measured theoretic way to try to, because we used probability measure somehow. We used very easy counting measure, but so it's like before what we discussed, we wanted to define some properties with a high probability, right? To consider some properties which hold with high probability. Now we would like to make topological viewpoint on this, and topological viewpoint, what you have to consider, this is a very standard, you would like to consider open dense subsets. If you have a topological space and you would like to see something like topologically generic, what you will see properties of open dense subsets or countable union of such. Okay, so this is why this is quite standard to consider this, right?
Oh, could you explain intuitively why it's max k and not min k in the definition of distance?
Well,
min would be 0.
0, right?
Oh,
mean it is the biggest ball. Consider it as a calligraphs. You have one calligraph, another calligraph. Both are labeled by the same set of generators, say A and B. Okay, and then you are at the origin and you start going. You see first stages, they are the same. You are happy. You go a little bit further, they are the same. You are happy, and you go maximum. Okay, and when it is you go, and after that you cannot anymore. This is your distance. Okay. Okay, great. So now it is very. This is just natural to consider this G delta dense sets in this topological space. Whatever topological space you have, it's kind of. If you would like can study a generic subset in this set space, then you consider this. But here, what is there is a little trouble with this approach. I will discuss this trouble in a minute, but first let us analyze a few examples. What we can say very briefly. I don't discuss in detail this space because you will see very quickly that there are some troubles with this approach. But okay, so what are limits? Probably it will help you to understand why this is such distance. So these are cyclic, for example, the first example, very easy. This is a cyclic group, right? And I say that in this space it converges to Z, which is a little bit strange, right? But what is cyclic group? On the level of calligraph, it is some cycle, right? And it converges, so K goes to infinity, right? So you have cycle bigger and bigger. When in this cycle you consider just a ball around the origin, you don't see that it is a cycle. You see just a segment, and it is the same segment you see in Z. Okay? So this is a basic picture, but it is helpful. And actually it is almost the same to see that if the group G is residually finite, then it is a limit of its finite quotients. So you learned residually finite today, right? Again, intuitively, what is a residually finite group? You fix it is finitely generated group. How you see that it is residually finite? You take a ball. The fact that it is residually finite will mean that you will find a finite quotient of this group such that the ball is exactly the same. So you keep the algebraic structure of the group in a finite quotient. Okay? This is just a definition, actually, a different way to say what is a residually finite group. And once you view it in this way, this is just obvious, right? Because whatever the ball you fix in your group, you will find a finite quotient which has this ball. So you put it in this convergent limit. Okay? Great. A different example, let us see this Reth product. It has this presentation, infinite presentation. You see? Infinite presentation. This is also one of the points of my lectures, that the infinite presentations are nice and interesting. Okay? They are not hyperbolic, but sometimes not very far. Okay? Okay, let us see this example. So this is a presentation, and it is a limit of these presentations. So you see, these are infinitely many, but here I take the same, but I cut infinite part. Okay? And actually, this is not clear. It is not clear from my definition. An argument is needed, but actually, this group contains F2 even of finite index. Okay, but this one, of course, not. So, but you see immediately that this group is a limit of this. Why you see it immediately? Because your relators here become bigger and bigger in length. So it's like so if you see a ball of given radius, you don't see all other relators. Okay. So So this is a general situation. We can write it like this. So if you have an infinitely presented group, then it is a limit in this space of finitely presented groups, which you just you take this and you cut the infinite path. Okay, so it is a general fact. These are just some examples of limits in this space, and this space is very interesting. A lot of work is done, and still has to be done. But let us make a right.
So here you're like talking more about like quotients. So like, but you always think about quotients of like some fixed.
Right.
You're saying that like something is limit of.
M is fixed, so free group is fixed. The generators are fixed.
Yeah. Okay. So like, yeah. So the distance between like quotients is like the. I mean, you think about like not only this finite group, but like actually how you get this finite group from the generators, right? Yeah.
You mean in this limit? In this limit, you mean?
Yeah, like for example, like the first one event, like.
We see, this is an important point. We see in this space, all groups are with a fixed generating set. Okay, this is really important point, because you can consider the same group but with a different generating set. It will not be the same representative of this space. Okay, and you are right. When I consider this limit, actually, it means that I fix a generating set here. And I take the image of it in the quotient. Right, right. The generating set is really fixed.
Because the distance that you define, it will depend on the generator.
Depend on the generating set. This is intuition I try to communicate with the balls in the calligraph. It really depends on the generating set. And when you consider like this ball is the same like this ball, it's really like labeled graph, meaning that really with respect to given generators. Okay. Great. So what is? Let us consider this remark. So the set of abelian groups is both open and closed in this space. So why? Well, just because to be abelian, you need only relators of length 4, right? You take generators and they have to commute. So relators of length 4. Well, this is for free abelian, but okay, if you take torsion also, but the intuition is the same. So just to be abelian, it's enough to consider the ball of radius 4, or even 2. Okay. So it means that when you have two groups, one is abelian and another one is close to it. And what it means, close to it? It means that you starting from some ball, right? So very quickly you get your commutator, you see it immediately. So your group which is close is also abelian. Okay? And other way around, so it is open and closed. So why it is? There are some other examples also. You can do the same game like I did very quickly for nilpotent of given class. Right, or solvable of given class.
And also both open and closed? Just for the
closed, I think. Exercise.
Those properties are carried in terms of.
Right.
Solvable groups or linear groups are close to each other in that distance.
Right. Why? If you fix the solvability length and nilpotence length, you have to fix. Why? Just because this nilpotence and solvability, it is defined by some word, commutators, right? Some fixed word. Here, the argument I gave, like for a concrete word, which is one commutator. But nilpotent and solvable, it will be a bigger word. But it means that once you are out of this ball, you should satisfy these properties, so you will be okay. So it's the same, but you have to fix the solvability length and nilpotence length. Great. So, but now if we see it, this is a very interesting space. We can study it and so on, and people do a lot. But if we see it from random, with this topological genericity point of view, then okay, this was our idea, very natural idea, right? But if you consider topological space and you consider an open set there, and you consider our open set is abelian groups, and you consider a dense subset, this is dense subset I'd like to study. But the intersection, the dense subset with open set, it is dense in the open set. This is just topology, general topology. Okay. So it means that actually, in my G delta dense set, I need to consider, for example, abelian groups only. And this is not very interesting, right? So, and of course, this is just an example. There are some other classes open, and so this topology is not very good with respect to this viewpoint. This is why there is people do a little trick. So, a little trick is this. So you restrict not like on some open set, but you restrict yourself on a class you like. Some generic class, and generic class in the sense you defined before, outside this topology. For example, why not to restrict only to hyperbolic groups? Because we proved already that in genericity model or in this density model we have a lot of hyperbolic groups. So why not to restrict just on hyperbolic groups and consider what is a G delta dense subset there when we restrict to hyperbolic groups and we take closure in this space. This is a very natural idea. Or even better, why not to restrict to torsion-free hyperbolic groups, right? So this kind of stuff one can do. And for example, this is a sample of results, quite interesting. So if we restrict ourselves on hyperbolic torsion-free groups in this space, and then we take closure, then there is a theorem saying that there is a generic subset in the topological sense having these properties. So, for example, what we can say, for example, yeah, very strange properties. You see, it gives immediately very strange groups, not hyperbolic at all, but they are in the limit, in the closure of hyperbolic groups. Okay? And these groups are not finitely presented, but they have very interesting properties, and this was the way to produce this kind of, to prove the existence of this kind of groups. But if you compare to another result, if you restrict not to torsion-free, but to this, just hyperbolic, then there is a G delta dense subset having which is made of torsion groups. So every element has torsion, and the group is infinite. So this is a kind of monster groups in this topological model. Okay, so it is an interesting approach. I discuss it only very briefly. Okay. Great. So again, the summary that you can define it. You should combine your knowledge and this natural topological idea to consider G delta dense subset, to discuss randomness from topological point of view, and the number of relators infinite in general. These are limits in this space. No small cancellation. And it depends on other models, as we saw. Okay? Yes?
So this distance function is actually like, if they are equal, right? With the, like literally equal inside the free group. But is there a way to weaken that distance to say they're isomorphic? Like a sort of, like for manifolds, there's this Gromov-Hausdorff distance that tells you when two are isomorphic or diffeomorphic. Is there a way to do it for groups?
Well, not in this space. In this space, it's really, they are isomorphic as labeled graphs.
Of labeled graphs.
Right.
Yeah, okay.
For example, if you remove labels, you can consider this, but then it will not be about groups, it will be just about graphs. Right.
So if the distance between two groups here is 0, does that tell you they are isomorphic or that they are the same inside of the group?
No, it's the opposite. Because the distance is 0. The ball. Almost the same, right. Mm-hmm.
So
But like they can be like abstractly isomorphic subgroups that are far away,
That
right?
are far away.
Right.
That's
That's
what
my
you were
question.
asking.
Yeah.
Right.
Like is there a way
Right.
to not have that, like isomorphic things actually being close
To
to
like
the distance?
actually
You would like to, yeah, there are some, right. You would like to consider the isomorphism equivalence relation with respect to this space, right? This is what we would like. And people study this kind of things. It's not easy. Yeah, because here you really, the fact that you fix the generating set, it restricts you a lot. Yeah. Of course, you can put, for example, I fixed M. You can consider all M's and put all these spaces together. It's possible, right? Because if I have M generators, I can add 1, 1, 1, 1, and I have 2 M generators, right? So I can put all them together, all groups somehow, but it doesn't add a lot. Actually, it's just a way to consider all these groups together, but it will not solve this thing. To do, you need something more.
Like a quotient? Or just something, some other construct?
You need something more. Mostly people in descriptive set theory or in logic, they study this kind of, yeah, right. Equivalence relation, what kind of, yeah.
I have a question. So basically, it shows that like if you talk about finitely generated like random groups, right? The properties are completely different from finitely presented.
Right.
Random groups,
Right.
And you can consider some classes of groups. Can you, for example, can you say what approach should be taken? Like we know that finitely presented random group does not act on trivial on a tree.
Okay.
Can this what is a random group acting on a tree? Like if you consider random group.
In this
can you use
infinite.
this or maybe you cannot use this? Just what would be an approach to random groups acting on trees?
Well, you cannot use it immediately. But what you are saying is really we need to consider. This is very natural to consider finitely generated groups, not necessarily finitely presented, and acting on trees. Okay, so this is some class, and on this class we would like to understand what is a generic group, right? So for models we discuss, and there is something else we will discuss, probably not today. Actually, we will have groups mostly with property T and things like that, which will not act. Okay, so even in this model, you see there is property T.
So this would not work like
No,
trees too.
no. So you have to really do something different. But you can use some ideas from here, but not exactly what is done. It doesn't give you an answer. Okay, I think it's time. Let me see. Right. So it's time to stop today, and tomorrow what we will do, we will go to this. So let us summarize. So we did genericity, we did density model, and we did this topological approach. And density, genericity, this was for finitely presented. Topological, it's more for finitely generated, but not finitely presented. But finitely presented are not very far from the story, because mostly these are limits of hyperbolic, right? And what we will do tomorrow, we will go to a completely different story of exceptional groups. I told you at the beginning, we will discuss typical properties and exceptional properties. So tomorrow we will start to discuss exceptional properties, and we will see what we can group properties and groups, what we can construct, and mostly it will be about infinite monster groups. Okay.